In this video, I will introduce a persistence of vision rotating display that is controlled by a Raspberry Pi Pico W. After a demonstration of its function, I will explain the structure of the device, go through the most important aspects of the design, and will explain how to reproduce the display. This is the third rotating display that I have designed and published. The goal was to upgrade the image quality, introduce animated images, to simplify the design, to use less components, and to make it easier to reproduce. I have introduced a new method for controlling the LEDs. The Raspberry Pi Pico addresses the LEDs in a multiplex process. As in previous designs, the microcontroller provides a web user interface through its Wi-Fi function. The display establishes a connection with the local Wi-Fi and can be addressed with its IP address. The user interface can be started in any web browser. I will use my mobile phone for this demo. I have called up the start page with the IP address of the device. In the middle of the screen there are 6 radio buttons for selecting the operating mode of the device. Below there are 5 buttons which are used to control the display. The first mode is activated when you start the device. It displays the SSID of the connected Wi-Fi and the IP address of the device. This allows the user to start the web interface for the control of the device. The second mode calls up an analog clock which displays the local time. I will show later how to configure the time zone. The third clock mode is a digital clock which displays the time, date, and the day of the week. The next mode displays the time and some logo or image in the background. The image can be selected on the configuration page of the device. The display uses openweathermap.org service for displaying the local weather conditions. The screen shows the time, temperature and humidity of the selected location. In the lower half, an animation of the weather condition is shown. In my case, there are clear skies outside. The last mode of the device simply displays an image. It can be both a still or animated image. Now I would like to move on to the configuration screen of the web interface. The first one allows for the configuration of the weather service. One can obtain a free API key from openweathermap.org, which needs to be entered here. Furthermore, the location of interest needs to be set. There is a configuration page for setting up the Wi-Fi connection. You can enter the SSID of your local Wi-Fi and the corresponding password. This information will be stored on the SD card and will be called up the next time you start the display. All images need to be stored uncompressed in order to allow for fast access. Therefore, I have included a SD card in the device for storing the image data. Files on the SD card can be managed with a file browser, which allows for wireless upload and download of files, but also for deleting, copying or moving files. The next page is the Image Manager. You can select the images for the various modes of the display and convert JPEG or GIF images to the proprietary image format of the device. I have called this format RDC, which means Rotating Display Color, as it is the same format that I used for my color display. As I mentioned before, the format simply stores the images uncompressed one after the other. The last configuration screen that I would like to show is the Time Zone Manager. Before I call up this page, I switch back to a clock mode so that you can see how the time changes. As you can see, you can select your time zone from this list. The time zone information not only includes the time difference to Universal Time UTC, but also information about daylight saving time so that the device always displays the right time. So let's change the time zone. I select India, for example. The display changes time accordingly. This concludes the demo of the device. Next, I would like to show you the structure of the display. I will turn off the electronics and will disconnect it from power. So here is the display PCB. You can see the LED row in the middle. It consists of 56 LEDs which are arranged edge to edge. They are displaced by a quarter of a LED width from the center in order to allow for interlacing, which I will explain later in this video. The microcontroller is located at the bottom of the PCB. The alternating field of the wireless power supply is weakest at this point, which avoids interference with the Wi-Fi function of the microcontroller. The rectification and voltage stabilization of the display is located above the microcontroller. While I used serial shift registers to address the LEDs in the previous models of the display, I use a different method in this version, namely multiplexing. The circuit consists of very few parts, 2 integrated circuits and some MOSFETs. The multiplexing method was the main challenge of this new model, as it has to be very fast. It benefits from the programmable I/O of the RP2040 microprocessor, as I will show later. The SD card reader is located at the top of the display. The SMD component can alternatively be replaced by an easily solderable SD card adapter. The last component that I would like to mention is the Hall sensor on the left side of the display. It is needed to create a spatial reference point. This is the structure of the display board. Let's now take a closer look at the power supply before I disassemble the device. The display consists of 2 assemblies, the display board and the power supply unit, which is located below. A wireless power supply is essential as not to disturb the rapid rotation of the display. The circuit is a Royer converter, which is designed entirely as printed circuit. The second circuit on this board is used to power and control the motor. The knob can be used to set the supply voltage and thus change the motor speed. To dismantle the display, 2 screws must be removed. You can now see the power supply board from above. You can see a large printed coil that transmits the power wirelessly to the display. On the back of the display you can see the receiver coil of the wireless power supply. In the center of this coil you see also a mount for attaching the motor axis. The display rotates at a speed of up to 10 revolutions per second. To avoid vibrations, it is necessary to carefully balance the mass distribution so that the center of gravity is exactly in the middle of the display on the axis of rotation. To achieve this, the components are largely arranged symmetrically to the vertical axis of symmetry. As a result, the center of gravity lies on this vertical axis. The 2 counterweights, which can be seen at the top edge of the display, are used to move the center of mass to the center of the disk. As already mentioned several times, the display uses a multiplex process to control the LEDs. This has the advantage that relatively few components are required. At the same time, however, the process presents a number of interesting engineering challenges. As the picture shows, the 56 LEDs are arranged in a matrix with 8 rows and 7 columns. The microcontroller selects the columns in quick succession and controls the rows accordingly. If this sequence is fast enough, the eye perceives a static image of all LEDs simultaneously. In order to achieve sufficient brightness of the LEDs, they are operated with a high peak current of up to 60 milliamps. This results in short, strong current peaks that need to be controlled and regulated accordingly. The rows of the matrix are connected to ground using a Darlington transistor array when an LED is to be switched on. The use of Darlington transistors relieves the outputs of the microcontroller and makes the current peaks fast. To activate a column, it is connected to +5 volts using a P-channel MOSFET. To be able to switch such a MOSFET, the control signal must reach +5 volts or 0 volts. As the microcontroller works with a 3.3 volt logic, a level converter is required. The 74HCT138 is used for this, which not only converts the logic level from 3.3 volts to 5 volts, but also works as a decoder. The microcontroller can select the output and thus the LED column to be activated via 3 control lines. Let's take a moment to look at the timing of the display to understand the speed implications. The display rotates at a frequency of up to 10 Hz. So every 100 milliseconds a trigger pulse is generated with the Hall sensor. The Hall sensor triggers an interrupt in which the microcontroller determines the exact time for one rotation and resets the pixel timer accordingly. In addition, the output of the LED data is reset so that it starts again from the beginning. The image is divided into 240 lines with 56 points each. The LED line must therefore be updated 240 times per revolution. The time for one pixel is therefore 100 milliseconds divided by 240, which corresponds to 420 microseconds. To display grayscales, 8 subpixels are output per pixel. In this way, the brightness of the pixel can be controlled in 8 steps. The time available for such a subpixel is therefore 52 microseconds. Within these 52 microseconds, the microcontroller must now call up the 7 columns of the LED row, one after the other, and switch on the LEDs accordingly. There are 7.5 microseconds available per column. So you can see that the pulses are really very short and that the controller has to perform the multiplexing extremely quickly. So let's now take a look at how this is possible. The RP2040 microcontroller has a very powerful unit for controlling the controller's inputs and outputs. It is called PIO, which stands for Programmable Inputs and Outputs. The unit can be programmed so that recurring sequences can be carried out very fast. It is therefore ideal for controlling the multiplexing of the LEDs. The microcontroller is relieved of as much as possible and only has to provide the data that is then output to the LEDs. Finally, I would like to make a few remarks about rebuilding the display. First of all, it is important that all design data is available in my public GitHub repository. This applies to the electronics and the entire software. Please note the license terms. You can use and further develop the data for personal purposes, but not for commercial purposes. The link to the GitHub repository can be found below the video. The electronics were developed with wired components so that the boards can be assembled by hand. The MOSFETs can be either classic wired components or SMD components. The SMD components are considerably cheaper, but more difficult to solder. The same applies to the SD card reader. This can also be installed as an SMD component and alternatively as an SD to micro SD adapter. It is glued on top the circuit board and the contacts are soldered by hand. The display is a 4-layer board. The 2 inner layers are used as grounding planes. This is necessary to minimize interferences from the fast current pulses. All other boards have only 2 layers. So much about the rotating display. Thank you for your interest and have fun rebuilding the display.